Okay, this will begin our discussion about Kerberos. Kerberos, as I mentioned before in the last class, this is an authentication service, and the authentication service is used for a set of workstations um, that are subscribing to server-based services. So, one idea here is that we can't trust a workstation to identify the user correctly to the user services. This is because a user can gain access to a workstation and masquerade as another user operating from that workstation, or the user could alter the network address of the workstation that they are working at so that um, it looks like requests coming from that workstation are actually coming from another workstation, the one that's being impersonated and the one that would actually be logged on with the authority to request those services. And then also there's an eavesdropping attack where an attacker can eavesdrop and then replay uh, the the captured packets to get access to a server. So those are the three main ideas. What Kerberos does is it provides a centralized authentication service um, that is there to authenticate the users to the servers and also the servers to the users. So there's this bi-directional um, authentication. The server needs to know that the user has the rights to access the services on that server, and the user also needs to know that they are actually talking with and getting services from the server that they believe that they're talking to. So Kerberos relies on symmetric encryption. No public key, uh, no public key in Kerberos. So the way that we'll proceed here is we'll talk a little bit about the background of Kerberos. Then we'll talk about Kerberos version 4, which is no longer used, but it's one way to explain Kerberos is to explain version 4 and then explain the differences between 4 and 5 to get you up to the current version, which is, in fact, version 5. So the requirements that Kerberos is designed to meet include security, you should not be able to impersonate another user. Uh, Also, reliability. For a large system that has all server-based services, reliability is critical because if you can't authenticate, if your authentication system doesn't work, then you essentially lose all of your computing services. It needs to be scalable. It needs to be able to grow with the size of the system. Large numbers of clients and servers need to be supported. And finally, it needs to be transparent. So the user, other than entering a password, should not really be aware that they're using an authentication service. So it should not burden the user. Okay, so let's start talking about Kerberos version 4. Kerberos version 4 uses DES as its authentication service. It consists of an authentication server, which knows all the user's passwords and stores them. We'll abbreviate the authentication server AS. This knows the user's passwords. And also the authentication server shares a secret key with each server. We also have the concept of a ticket. When the authentication server authenticates a user, it creates a ticket, and this ticket contains the user's ID and the network address, and then also the server's ID. A ticket granting service, or a TGS, this issues tickets to users that are authenticated to the authentication server. Every time the user needs to access a new service, the client applies to the ticket granting service and uses that ticket to authenticate itself. So it's used by the client every time he or she needs to access a new service. The ticket granting service will then grant a ticket for that particular service, and then the client saves each one of these tickets and uses it to authenticate each time it's going to request that service. So one problem that we have is that we need to deal with the lifetime associated with the ticket granting service. If we make it very short, then the user repeatedly has to enter their password, but if it's too long, then obviously an opponent or an adversary has got more opportunity to do a replay attack. So the network service has to be able to ensure or prove that the person using the ticket is the same as the person to whom that ticket was issued, and the servers also need to authenticate themselves to the users. Okay, so to start to describe the way that these message exchanges are going to take place, we have a key here with some abbreviations for some of the entities that will be doing the communication, as well as some of the data structures that are being communicated. So what we'll do is we'll start out with sort of a simple authentication dialogue. We'll talk about some problems, and then we'll add some complexity to it to solve those problems. So we can imagine that we are in some network environment, and in the environment we have clients that are applying to services for services, and theoretically any client can apply to any server for any service that that server can provide. And so the risk is here that a user would impersonate another user with some higher level privileges, or maybe they can obtain information that they're not supposed to get. So in order to deal with this, the server has to be able to confirm the identities of the clients who are making these service requests. Each server is required to do this task for every interaction that it has with a client. But of course, in an environment with many clients, this can potentially put an undue burden on the server. So an alternative to this idea is to use an authentication server. The authentication server knows the passwords for all the users, and it's storing these passwords in a centralized database. And it also shares a secret key with each server. So we could have a dialogue that looks like this. For example, client can initiate contacting an authentication server, sending a message with that client's ID and the password for that client and the server ID. And then the authentication server could issue to the client a ticket, and then the client can then turn around and talk to the server with the client's ID and the ticket. And here the ticket could be an encryption with KV. This is the key shared by the authentication server and the server itself. And what would be encrypted is the user's ID, so it's the client's ID, the client's address, and then the server ID. So now the server gets this information. The user logs in, requests access to the server. The server gets the ticket. So by sending the ticket, by the client sending the ticket to the server, it's applying for access to the service that server's providing. So the server then has to decrypt the ticket and make sure that the ID that was encrypted, remember this is encrypted by the authentication server with a key that is only shared between the server and the authentication server, so the client can't decrypt this message even though the client is the one forwarding it onto the server. So now the server makes sure that this ID is the same as this ID. So the ID that's in the ticket here is the same as the ID that the client has. So the ticket is basically preventing a forgery. Because we have the server's ID in the ticket, then the server can verify that it's actually decrypted the ticket properly, or that it hasn't been changed somewhere along the way. The client's ID is in the ticket to make sure that the ticket, which was issued by the authentication server, is associated with that client, and the address of the client is there because some other user could capture the ticket while it's being transited, while it's in transit, and then use that ticket and the name of IDC, and then transmit a message in this form to try and get access to the user from another workstation. So in order to prevent this attack, the authentication server puts the network address from which the original request came, so that you can't use that ticket from another network address to try and get access to the services that are being legitimately requested. In other words, this associates the ticket not only with the user, because it's got the ID of the user on the client, but also with the specific workstation, because it's got the network address of that. So this is a reasonably good scenario, because some of the authentication problems that we would have in the type of environment that we're describing are solved, but there are a couple problems that remain with this scheme. So let's talk about those problems. One, we want to minimize the number of times that the user has to enter their password. So if each ticket can only be used once, then every time the user logs on to their workstation, say they're using a mail server, so they want to check their email from the mail server. They have to get a ticket for the email server, and if they're doing this, as often as we all do, many times a day, each time they want to do this, they have to re-enter their password. So that's one problem, is that the user has to enter the password every time a service is requested. So we're placing undue burden on the server, and we'll improve this by making the tickets reusable. The other problem is that you may notice that this initial communication has a very severe problem in it. Specifically, the password in this message here is being sent in the clear. It's being sent in plain text. So we'll call this problem A. Problem B. Password sent in plain text. Clearly, that's not acceptable. So let's enhance this scheme to try and solve these problems. One thing that we're going to do is we're going to introduce a ticket granting server. Which we've already talked about a little bit. So here's how the new scheme will work. This communication will take place just once per logon session. The client will communicate with the authentication server, that client's ID, and the ID of the ticket granting service, and the authentication server will respond to the client with an encrypted message, encrypted with the client's key, a ticket for the ticket granting service. So there's this new service, ticket granting service, that's issuing tickets to users that have already been authenticated to the authentication server. Now, once per each type of service, the client will contact the ticket granting service, sending the client's ID, the server that it's trying to reach, that server's ID, and then the ticket that it's been issued by the authentication server for the ticket granting service, and then the TGS will issue to the client a ticket for the service V. And then once per session, so say every time you want to check for mail on the mail server, the client contacts the server with its ID and the ticket that it got from the ticket granting service to use that service. So we've got two tickets. Let's look at the structure of those tickets. The ticket that the client gets for the ticket granting service is an encryption with the TGS's key containing the client's ID, the network address, the ticket granting service ID, TS1 and lifetime 1, where lifetime is going to define the lifetime of the ticket. How long is that ticket going to be valid for? And TS1 then is a timestamp, so the date and time at which the ticket was issued. So with the date and time and the lifetime, the length of time for which it's valid, you can reuse this ticket for some period of time. The ticket that is being issued by TGS to the client for the server, this is encrypted with KV. That is the key that is shared between the server V and the authentication server, or the TGS, and that's going to be, the message will contain the client's ID, the client's address, the server ID, so that this protects against any kind of changes that happen to this. The server needs to be able to find its own ID in the message, a timestamp, and a lifetime. Same idea as before. So now the TGS, the ticket that the client has with the ticket granting service, has some lifetime associated with it, so that you don't have to go back to this first step here where you're actually applying for that ticket. And the ticket with the server, which gives you access to the service, which you got here, has a lifetime associated with it as well, so that each time you want to use that service up until the lifetime has expired, you only need to do this exchange. Okay, so some improvements here. We've got better security than we did in the initial idea, but there's still two problems associated with this scheme. The first problem has to do with the lifetime associated with the ticket granting service ticket. Now, if we make this lifetime short, then the user has to keep entering their password, right? Because, again, the user, to get this TGS, has to authenticate. However, if we make the lifetime very long, then there's potential for a replay attack. So the way this attack would work is that the opponent would listen on the network and get the ticket granting service ticket, and then if the user who was legitimately using that ticket logs out, but the lifetime of the ticket hasn't expired, then the attacker can forge the network address, because remember, the network addresses have to match, and send out this message and apply for services that user apply for services while impersonating the user who legitimately obtained the ticket granting service ticket. A similar idea would be for the attacker to use the service granting ticket before it expires. If so, again, you can impersonate that user either with the TGS ticket or with the service ticket, depending on what you're trying to do. So that's one problem, the lifetime of these tickets. The next problem is that it would be beneficial if the servers were authenticating themselves to the users. Otherwise, the user does not know. They could be communicating with a false server. A false server could pretend to be the real server, get the user's information, either deny access or provide invalid services. So we need to make some improvements. If we think about the problem of the ticket granting tickets, the problem there is to make sure that the entity presenting the ticket is the same as the client who was issued the ticket, and that it's not someone else who stole the ticket and is still using it because the lifetime hasn't expired yet. So what we'll do here is we'll have the authentication server provide both the authentication server and the ticket granting service a secret that they can share. We'll do this in a secure manner, and now the client can always prove that they are the actual client to the TGS by providing that secret information in a secure manner. So in order to do this, an encryption key will be used, and this will be called a session key. So let's look at the way that these messages would. So the problem, let me write the problems down. Problems are that an attacker can use the TGS ticket or the server ticket before it expires by forging the network address. The second problem is that the servers should be required to authenticate with the client. Okay, so this brings us to what would be the version 4 Kerberos message exchanges. We've built it up to that point. So here's what that looks like. Kerberos v4. 1. The client is going to contact the authentication server, sending the client ID, the ID of the ticket granting service, and a timestamp. The authentication server responds to the client, providing a message that's encrypted with the client's key for the ticket granting service. With the client's key, and it's providing, so this is what it's encrypted with, but it's going to provide a key for that client associated with the ticket granting service, the ID of the ticket granting service, a timestamp, a lifetime, and a ticket for the TGS, where the ticket for the TGS now will look like this. So it's encrypted. It is encrypted with the key for the TGS, and it's going to contain this same key will be included, the client ID, the client address, the TGS ID, timestamp, the lifetime, okay, so now this is the authentication service exchange to get the TGS ticket. Now, the client can talk to the ticket granting service, or ticket granting server. That initial communication with TGS will include the ID of the server with whom the client wants to utilize, the ticket for the TGS, and an authenticator for the client. The TGS will respond to the client with a message encrypted with this key that the client shares with the ticket granting service, a key for the client with the server, the ID of the server, a new timestamp, and a ticket for the server. So to look at the structures that are involved here, the ticket for the TGS, we've already discussed that. The ticket for the server is encrypted with the server's key, and it's got the key that the client is sharing with the server, the client ID, the client address, the server ID, a timestamp, and a lifetime. The authenticator is encrypted with the key that the client is sharing with TGS, and it contains the client's ID, the client's address, and a timestamp 3. So these two steps, these are the ticket granting service exchange to get a service granting ticket. So get a service granting ticket. Now the client and the server can exchange information to get access to the service. So the fifth message passing here will be from the client to the server. The client will present the ticket that it was issued and the authenticator. And the server will respond to the client with a message encrypted with the key that the client and the server share. That message will be timestamp 5 plus 1. This is giving mutual authentication. And we know what the ticket and the authenticator look like here. So this is the client and the server authenticating. So we have several messages that we've added in here, some additional information that we've added in. Notice that we've added in a timestamp to this first message. This allows the authentication server to check and make sure that the message is not an old message. Message 2 now has several of the elements of the ticket that are accessible to the client. So now the client can confirm that the ticket is for the ticket granting service, and it can learn about when it's going to expire. Now that the client has the ticket and a session key, it can talk to the TGS, so that's what happens in this next exchange here. The client sends the message to the TGS with the ticket and the ID, but also there is this authenticator. So the authenticator has the client's ID and the network address, and also a timestamp. And the authenticator can only be used once and has a very short lifetime. So now the ticket granting server can decrypt the ticket using the key that it shares with the authentication server, and then that ticket indicates that C, the client, the user on the client C, has this session key K sub C TGS. So the ticket basically is allowing anybody who has this key KCTGS, or it's saying that that person who has that key must be the client C. So it's that type of authentication. The ticket granting service uses the session key to decrypt the authenticator, and it can check the name and address from the authenticator and compare it against the one in the ticket, and the network address from the incoming message. So there's this comparison between what's in the authenticator, which can only be used once and has a short lifetime, and what is in the ticket. And if all of that matches, now the TGS knows that the sender of the ticket must be the ticket's real owner, the person to whom, the entity to whom the ticket was issued. So the authenticator is basically providing encrypted information that should match the information in the ticket. The next message, message 4, looks a lot like message 2. It's encrypted with the session key that TGS and the client share, and has the session key that the client and the server share. It's got the identification of the server, the timestamp of the ticket, and the ticket also has the same session key embedded in it. So this gives the client a reusable service granting ticket for the server V. And then down here in message 5, the client can present that ticket to the server. But when it does that, it will also send an authenticator. And now, in a similar means as we described before, the server decrypts the ticket, recovers the session key, and decrypts the authenticator. So now the client has authenticated to the server. Now, if mutual authentication is a requirement, then message 6 will take care of that. What's happening there is the server takes the value of the timestamp from the authenticator the client sent, from this authenticator C, adds 1 to it, and then encrypts it with the key that is being shared by the client and the server, and sends that back. So that gives the idea is that only the server could have decrypted the authenticator and gotten that timestamp out. So now you just perform a small function on that authenticator, and that authenticates the server to the user. Notice that once this process is concluded, the client and the server now share a secret key. So that key is used to encrypt messages in the future when the new when those two entities want to communicate. Okay, so there is a concept of a Kerberos realm. A realm is a set of nodes that share the same Kerberos database. The database itself resides on a centralized computing system. This computing system should be physically secured. There may also be a read-only copy of the database on some of the other Kerberos computer systems, but all the changes to the database have to be made on the master computer system. And of course, any changes to the database would require that the person doing the changes knows the master password. So this is basically the crown jewels of the Kerberos system. We also have a concept of a Kerberos principle. A Kerberos principle is just a service or a user that is known in the Kerberos system, identified by its principal name. So there's three parts to the principal name. There's a service or a username. An instance name. And a realm name. Now, it is possible to have requests for services go from one realm to another realm. There's a mechanism for doing this. So if you're a user and you want to get service from a server in another realm, you need to get a ticket for that service. So the basic idea here, you are, say, in realm 1, you're a client, and of course in your realm you've got an authentication server and a TGS, and then there's another realm, and we'll call it realm 2. There's a server, also of course an authentication server, and a TGS over here as well. So the way that this would happen, the way that these requests would be made, the client would initially contact the authentication server with the client's ID, the TGS ID, and a timestamp. The authentication server is going to respond to the client with a message that's encrypted with KC. It's going to contain KC TGS, the identification of the TGS, another timestamp, a lifetime, and a ticket for the tag generating server. Number these. At that point, the client can use its ticket with TGS, so it's going to send to the TGS the ID of the remote TGS that it wants to contact. It's also going to send along its ticket for the local TGS and an authenticator. Now the TGS responds to the client. This message is encrypted with the key that is shared by the client and the TGS, and it will contain a key for the remote TGS and the client, the ID of the remote TGS, a timestamp, and a ticket. It's timestamp 4 because timestamp 3 is actually in this authenticator. Now that the client has a ticket for the remote TGS, it can contact the remote TGS. It's going to send the ID of the remote server that it's requesting services for. It's going to send its ticket for the remote TGS, the ID of the remote TGS, the timestamp, I'm sorry, it's just going to be the server ID for this communication. It's going to be the server ID, the ticket, and the authenticator. Now the remote TGS responds an encrypted message with the key that the client and the remote TGS server share. It'll send a key that can be shared between the client and the remote server, the ID of the remote server, a timestamp. We're up to timestamp 6 here because timestamp 5 is in this authenticator, and a ticket for the remote server. This will now the client's got a ticket for the remote server, so it can contact the remote server with its ticket. And an authenticator. And so in this manner, a client can request services from realm to realm. Okay, so that is version 4 Kerberos. Now let's look at some of the differences between version 4 and version 5. So there's two areas of limitation that the changes in version 5 are set up to address, and one of them is some of the environmental shortcomings. These include the fact that you're dependent on an encryption system, internet protocol dependence, problems with message byte ordering, some more problems with ticket lifetime, authentication forwarding. We'll go into each one of these in detail. And inter-realm authentication. And then there's some technical shortcomings, specifically double encryption, PCBC encryption, session keys, and password attacks. Okay, so I mentioned before that version 4 requires the use of DES, right? So this became a problem. Originally, this became a problem because there were export restrictions on DES. So you couldn't use, since Kerberos was dependent on DES, and you couldn't export DES, you couldn't use Kerberos outside of the US. But now we know also that there's problems with the strength of DES. So in version 5, there is a encryption type identifier so that you can use any encryption method that you want. Keys are tagged with a key type and a length, so you can use the same key in different algorithms. And so there's a lot more flexibility in terms of how you do encryption in version 5 than the very strict methods prescribed in version 4. So that's what's up with the encryption system dependence. Internet protocol dependence. In version 4, IP addresses were required to be used. So you couldn't use, for example, ISO network addresses or MAC addresses or anything like that. In version 5, similar to the techniques that were used with the encryption, network addresses are tagged with a type and length. So now any type of network address can be used. You're not restricted to using IP addresses. In terms of message byte ordering, in version 4, the sender of the message can choose the ordering, the byte ordering of the messages, and it tags the messages to indicate the significant byte in the lowest address, or the most significant byte in the lowest address. And this is this just it works fine, but as time went on, there became more established conventions that were used. So in version 5, there's byte ordering is defined, or is set up as defined in the ASN.1 and basic encoding rules BER, so that there's no ambiguity in terms of byte ordering. In terms of ticket lifetime, in version 4, the lifetime of the tickets were encoded in an 8-bit quantity in units of 5 minutes. So the maximum lifetime was a little over 21 hours. And for some applications, this is not adequate. For example, if you're running a simulation that takes a really long time, it also requires valid Kerberos authentication while it's executing. So this was a problem. In version 5, the tickets include explicit start and end times so that you can have an arbitrary lifetime to a ticket. In terms of authentication forwarding, version 4 did not permit a credential that is issued to one client to be forwarded to another host and used by some other client. This would enable a client to access a server and have that server access another server on its behalf. Version 5 does permit this. And then inter-realm authentication. In version 4, interoperability. If you want to have, say, some number of realms interoperating, then that would mean that you would have, if there were n realms, then you would have on the order of n squared relationships in a similar manner to what we were talking about before. And version 5 changes this relationship, or the way that these relationships are basically it has a method that allows fewer relationships to be maintained. We'll talk a little bit about that. But over to the technical shortcomings first. So the double encryption. One of the things that you may have noticed is that tickets that are provided to clients are encrypted twice. They're encrypted once with the secret key of the target server, and then again with the secret key known to the client. And this is just unnecessary and computationally wasteful, so version 5 does away with this. In version 4, there was what was prescribed was a non-standard mode in DES, which is this PCBC. It's propagating cipher block chaining. This has been shown to be insecure, and so version 5 provides better mechanisms and uses standard cipher block chaining mode for encryption. So that's this PCBC. In terms of the session keys, every ticket has a session key that the client uses to encrypt the authenticator that gets sent onto the service for which the ticket has been issued. The session key also can be used by the client and the server then if they want to pass messages back and forth in a secure fashion. But since the same ticket can be used repeatedly to get service from that particular server, there's a risk of a replay attack from an old session to the client or the server. So in version 5, to mitigate this, the client and the server can set up a sub-session key, which is to be used only for that one connection, and a new sub-session key would be issued every time there was a new access from that client on that session. Finally, password attacks. Of course, there's vulnerability to a password attack. The message from the authentication server to the client has encrypted material, and it's encrypted with a key that's based on the client's password. So if an opponent is getting these messages, he can use them to try and he can try various passwords to try and decrypt them. And if he gets something that is of the appropriate the appropriate structure, then that's an indication that the client's password has been compromised, and he can use it again, right, to get authentication credentials, masquerading as that client. Version 5 provides a mechanism called pre-authentication, which makes password attacks much more difficult, although you can never completely mitigate them. So we can look at the message exchanges for version 5 to see some of the differences. So, as we've seen before, everything is initiated with the client contacting the authentication server, but now there's going to be an options field that is in this message. The ID of the client, also the realm of the client, is included in this message now. As before, the ID of the TGS. Times, remember before we were using a timestamp and then a lifetime. Now it's beginning and ending time, so that we can have arbitrary lifetimes, and a nonce. The authentication server will respond to the client. The message will include the realm of the client, the ID of the client, a ticket for the TGS, and an encrypted message encrypted with KC that includes the key that the client will share with the TGS this times field, the nonce, the realm of the ticket generating server and its ID. Here the ticket for the TGS is an encryption with the key for the TGS that includes a field for flags, the key that the client and the TGS are going to share, the realm of the client, the ID of the client, the address of the client, and times. Step 3 now, client communicating with TGS. There's an options field, an ID of the server, times, another nonce, the ticket for the TGS, and an authenticator. TGS will respond to the client with a message that contains the realm of the client, the ID of the client, a ticket for the server, and an encrypted message. This will be encrypted with the key that the client and the TGS share. It will have a key for the client and the server, times that new nonce, the realm of the server, and the ID of the server. The server ticket looks like this. It's encrypted with the server key. It's got a flags field, sorry, that's not right. The key that the client and the server will use, the realm of the client, the ID of the client, the address of the client, and times. And the authenticator from up here is an encrypted message. It's encrypted with the key that the client and the TGS share, and it's got the client ID, realm, and a timestamp. Finally, the client can now contact the server. The initial communication will have an options field, the client's ticket for the services on the server, and an authenticator. Server responds to the client with a message that is encrypted with the key that the client and the server share. It's going to have that timestamp, the sub key. Now this sub key is generated every communication, and a sequence number. This authenticator is encrypted with the client server key, contains the ID of the client, the realm of the client, the timestamp, the sub key, and the sequence number. So the sub key here is what the client wants to use for an encryption key to protect a specific session. If that field is omitted, then KCV is used. The sequence number is also optional. It specifies the starting sequence number to be used by the server for messages sent to the client. So this gives some protection against replay attacks. Now we have these flag fields. Let's talk about some of the flags that can be used in those fields. There's the initial flag. So the initial flag means that the ticket was issued using the authentication server protocol, and it's not issued based on a ticket granting ticket. Pre-authent. So during the initial authentication, if the client was authenticated by, for example, a KDC before the ticket was issued, this pre-authentication flag would be set. If this is hardware authent, and this is initial authentication for using hardware that would be expected to only be associated with a specifically named client. So a piece of hardware that's specific to a client, the hardware authent protocol is called out. Renewable, the renewable flag tells the TGS that the ticket can be used to get another ticket, a subsequent replacement ticket that would expire later. May post date. This indicates to the TGS that a post-dated ticket can be issued based on the ticket granting ticket. Ticket granting ticket. May be used to obtain a post-dated ticket. Post-dated simply indicates that the ticket was post-dated. The invalid flag indicates that the ticket is invalid. And must be validated before use. Proxyable. This means that a new service ticket with a different network address can be issued based on the existing ticket. Forwardable. Forwardable flag indicates, again to the TGS, that a new ticket granting ticket with a different network address can be issued. So it's the same as the proxyable, except this is for a ticket granting ticket. There's the proxy flag. Indicates that the ticket is a proxy. And there's the forwarded flag, which indicates that the ticket has been forwarded or was issued based on an authentication that involved a forwarded ticket granting ticket. Okay, so that sums up the differences between 4 and 5, and that'll conclude the discussion on Kerberos.